All right, so a couple more things just to wrap this up, and then we're gonna move into the actual reduction potential charts. When we look at our feller here, one thing I want you to see is this is the side where the anode is. All right, this is the side where the anode is. This is the side where the cathode is. And so there's a way to do this shorthand. You know, we don't want to have to go out there and say over and over and over again. Okay, so we got a reaction, we got a half reaction, we got another half reaction. And so what I want you to see is, look, we've got this metal that's here. We've got the anion of that metal here from the anode side. We've got the the cation of this metal that's right here on that cathode side. And it's always it's easy to remember. If you know the Greek alphabet, you know that A comes before C, so put anode before you write cathode. So always we're gonna do the oxidation side before we do the reduction side. Now, what I want you to see is I'm gonna do some quick erasing. So look at my drawing as is. I'm gonna erase, beep, 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 and I'm gonna erase. Beep, 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 beep. And you can see what's left behind. All right, what we have is we have the aluminum line that kind of represents, to my head, it represents the sides of the bar of the metal. We have the aluminum ion, line. So I'm gonna make these longer so you don't get confused here. Line. I like to think of that as a separation of the two beakers. Cu positive 2, line, Cu line. So you can't imagine this being the metal, this being the solution of the beaker, the metal. What we say, this is what we call cell notation. So this is how we notate what the cell is. So if you get given that, you can already assume you know which side is the anode, which side is the cathode, and life is good. All right, no big deal. Now, you might be telling yourself or asking yourself, well, what if I get given a scenario where I have aluminum ions, which could become aluminum 0 plus 3 electrons. And in that same solution there, we had copper ions, which could become copper 0 plus 2 electrons. How do we know? How do we know which side is where the reduction is going to take place and which side is where the oxidation is going to take place? You'll get a handy dandy chart. Another little handy dandy chart. This is what's called the standard reduction potentials in aqueous solutions at 25 degrees Celsius. There's that standard ambient temperature and pressure right now. One thing I want you to know is this is if everything is a 1 molar solution. So we got 1 moles per liter of solution there. So we get ourselves a handy dandy little chart to look at. And what I want you to see is we have ourselves a bunch of reductions. So let's look at this close. Hopefully it zooms in. We have ourselves a bunch of reductions. All right, and so I can see my wrinkles here. A bunch of reductions taking place across the way. So everything's gaining electrons. Over here, you can see there's reduction potentials. And there's different values there. This is where you gotta be a little bit, this is where I'm explaining this in class better, but this is where you gotta be a little bit understanding of what's going on here. Everything has a positive charge. Everything that has a positive charge is gonna be able to be reduced. It's gonna have a reduction potential. And you go, but these have negatives. Well, here's the deal. What we do is we base everything on hydrogen's reduction potential. So how good is hydrogen reducing? So if we look at just hydrogen itself, we come over here and we see that, water, but the hydrogen itself, the hydrogen from the water, is being reduced and it has a 0 there. So the way to think about this, somebody asks you how attractive you are. Somebody asks you how attractive you are. You're like, I don't know. Based on what? Based on what? And then they come by and go, oh, I got an idea. And they find a human being and they say, this is the average, they're small apparently, this is the average human being look that we're gonna call average. This is the person we're gonna base everything on. So let's say me, I am picked as average. I am what they consider to be the standard, standard reduction potentials. I am the standard at which everything is based on looks-wise for males. And so now you go, how attractive are you? And somebody comes by and goes, oh, according to the HAECKER'S scale, I'm this much more positively attractive than him. This is my ability to attract other people to me. And somebody else comes by and goes, oh, I'm less attractive than him. I'm a negative value in terms of his attractive abilities. Does that make sense? So you can't really say, okay, how attractive are you? Well, in a room full of unattractive people, you might be really good looking. In a room full of people like Chris Hemsworth and Tom Cruise and whoever else you want to pick as beautiful, you go, oh, I'm pretty ugly. It's okay. And so what happens is everything here is based upon the, what we, geez, that upset me. Is based upon the She, the standard hydrogen electrode. Oh wow, 8 minutes in, I can't stop. The standard hydrogen electrode. And so the standard hydrogen electrode is what we say zero. That's the zero potential for reduction. Now, why they pick that? I don't know. Everything above it has a positive reduction potential. It's greater in reducing than hydrogen is. Everything below it has a negative reduction potential. Even though it's still reducing, it has a negative reduction potential. Make sense? Hopefully it will. So we look over here and we look at aluminum. Now I know my little chart here, you have your own, but my aluminum right here. Aluminum has a standard reduction potential of negative 1.66 volts. So this guy's voltage is negative 1.66 volts. There we go. And we look at copper. And we look at copper, and copper has a reduction potential of 0.34 volts. So voltage of copper is 0.34 volts. So now what that means is copper has a greater reduction potential than aluminum. The copper ion is going to win. So what's going to happen when put together? The copper ion is going to stay as is. This guy's going to flip. So we're going to get aluminum plus copper ions is going to make copper plus aluminum ions. Ooh. And now what happens? Remember, the voltage of copper is 0.34 volts. I flipped this, reminds me of Hess's law. I flip this becomes a positive 1.66 volts. So that means the cell, this cell that I've just made has a net voltage of, it looks like, 2.0. Yes, 2.0 volts. So I just made a 2-volt battery. A 2-volt battery. We're going to talk about how much work that's going to do later, but that's a 2-volt battery. Now, remember what I said? These are all at 1 molar. So remember, as the battery goes on, as that battery moves on, what ends up happening is the molarity goes down. And as the molarity goes down, the voltage is going to go down to 1 molar concentration. The less polar honors, the less voltage, the less energy you have per coulomb of charge. So that's gonna go down. So that's why your battery begins to die, is that we end up having a decrease in our ions here, and especially the big pullers here, the ones that matter. These guys go down in quantity. And so hopefully that kind of makes sense. Now, with that being said, this is the voltage, the potential energy we have, the joules of energy we have per coulomb of charge that we can now put out into the world and use as energy. We're going to come back to a cute little formula called delta G is equal to NFE later. But what this is delta G. Remember, if delta G is negative, it's spontaneous. Moles of electrons exchanged. What do we have here? 6 electrons. Fancy F is Faraday's constant, greatest scientist of all time, one of Michael Faraday. We have ourselves Faraday's constant. We're going to talk about that. We're going to talk about what it means, but right now, just as a constant, leave it alone. Moles of electrons exchanged times a constant times the voltage. We have one more thing we got in here, negative. So what we have is, if we want to find out how much free energy is released, we take the moles of electrons exchanged and multiply it by our voltage. This is our voltage. E naught is our standard voltage. And a negative times a positive, positive, positive is going to give us the energy that is available to do work. The free energy that's available to do work.